Alright, next we're going to look at how to use the second derivative to find local extrema. Remember that local extrema refer to a local min and a local max. And what we did before was we used the first derivative to find the local min and the local max. Recall that we set the derivative equal to 0, we solved, we made a sign diagram, we looked for where the first derivative sign changed. That's how we found our local extrema. Well, to introduce this, suppose we have a function that looks like this. This is a function f, okay? And our point of interest is up top here. Now, at this point of interest, we can see that it's clearly a local max, right? So let's just identify this here. All right, we know that this is a local max just by looking at it, right? Okay. Well, at that top point, we know that the first derivative is equal to 0. And notice that the second derivative would have to be less than 0, right? The second derivative is negative because it is concave down. So we can summarize this by saying that if our point here of question, all right, trying to confirm if a certain x value is an actual local min or max, well, you can use the second derivative, all right, by simply looking at its sign. If the second derivative is negative, that means as long as the first derivative here was equal to 0, it's guaranteed to be a local max. So let's just jot that down. So what I'm saying is this. If the first derivative is equal to 0 and the second derivative is negative at a point, and again, this is the point we're referring to, all right, then that point is a local max. Okay. Likewise, if we have something that is concave up, okay, and so this is another sketch of a possible graph f. At that point, we know the first derivative is 0, and we know in this region here, that point is in a region that's concave up, so the second derivative is positive, okay? So we can say that this point here is going to equal a local min, okay? So let's summarize that. So if the derivative is equal to 0 and the second derivative is positive at a certain point, and again, this is our point we're referring to, then that point is guaranteed to be a local min. Let's look at an example of this in action. Okay, so we're looking to find local extrema using the second derivative. All right, so we're told specifically we have to find these values using the second derivative. Well, we still need to find the first derivative, so 3x squared minus 12, okay? And you're still going to set this first derivative equal to 0 and solve. All right, so factor out a 3, left with x squared minus 4. All right, we know this is going to produce x plus 2, x minus 2. From there, we know that we're going to have critical points at x equals negative 2 and x equals positive 2. But the difference is, guys, we're now going to jump right to the second derivative. We're not going to make a sign diagram for the first derivative. So please make note that there's no f prime sign diagram needed, okay? Because we're looking to use the second derivative. So this is what it's going to look like. Find your second derivative. We know that is going to be 6x. Now, what we're going to do is we're going to take these values of negative 2 and positive 2, and again, we know that at each of these values, we know that the derivative was equal to 0, right? That came from setting our derivative equal to 0, right? So we're now going to take each of these values and we're going to plug it into the second derivative, okay? So if I plug negative 2 in, I'm going to get negative 12. If I plug in positive 2, I get positive 12. So let's think about what this is telling us. All right, at this point, negative 2. Well, we know that it's either going to be a min or a max because, well, we at least know that it's a critical point because the first derivative was 0. Now, because this is negative, that means it's in a region that is concave down, okay? So because we know the slope of the tangent line is 0, and because we know that it's in a region that is concave down, All right, x equals negative 2 is a local max because f double prime of negative 2 is less than 0. It's important that you get in the habit of writing out a sentence like that. On AP questions, all right, it's not enough to just draw a picture. You're going to be expected to write out not only the fact that x equals negative 2 is a local max, but you also need to justify why. So the x equals negative 2 is a local max. That's worth a point typically. And then this because piece is worth another point. So you have to say because the second derivative with negative 2 plugged in is less than 0. Okay, I can't stress that enough. Likewise, for this other piece, all right, we can see this is positive. Okay, so that means that it's in a region that is bent upward, right? It's concave up. So we know that the derivative is 0, it's concave up. So that means that at x equals 2, this is a local min. All right, please excuse my kids in the background, they just got home. X equals 2 is a local min because f double prime of 2 is greater than 0. Okay, so anytime it's in a region that's concave up, it's going to be a local min. Okay, so that's how you would use the second derivative. That's all for now. Bye-bye.